Let's get full screen here. Get started to talk about the rules of logarithms, which is where we're going to head. Get this out of the way. And it's a nice, bright, sunny morning and good time to talk about logarithms. All right. So I start my classes, whether it's Algebra 1, Pre-Cal, Algebra 2, Pre-Cal, even Calculus. Often I start my classes with the same thing on the board every single time. And so if you want to pause the video and answer this question, the value of the exponent that you put on top of a 5 to get the quantity 25 is a 2. If that's how we did mathematics, we wouldn't get too far. It took me a while to write that. So we communicate symbolically. It's a language. And if you don't understand what's being asked, you can't answer the question. So take a moment, write down what you think I wrote symbolically. And if you're like most of my students, you probably didn't write what this sentence suggests you should write. So let's do it. So most folks would say, oh, 5 squared is 25. That's not really what I wrote. The value of the exponent. That's what a logarithm is. Well, logarithms are values of exponents that I put on top of a 5. Insinuates that that's a base. To get the quantity 25 is maybe written as a 2. That's really what I communicated to you. All right, and so you have to, your brain, when your brain sees this communication, you're looking for an exponent. So probably the most important exponential function, mathematics, is e to the x. There's another one out there. I don't know it. It could be. The discipline continues to evolve. But I ask my students to memorize, absolutely memorize some key values, some approximations. E is approximately 2.71. E to the 1.1 is a little bit bigger exponent than 1, and 2.7 to the 1, I think we should know, 2.71. So e to the 1.1. It's an approximation, 1.1. Gets you 3. E to the 0.7 gets you 2. E to the 0 is 1. And we studied negative exponential values, and they're really reciprocating function. So e to the negative 1.1, 1/3, e to the negative 0.7 equals 1/2. And when we're graphing e to the x, we use these approximations in my classes to get a feel. And once we get a feel for these numbers, then we get a better feel for the values by looking at the graph of the inverse of e to the x. Got its own button on a calculator, e to the ln of x. Let's bring the cart down, talk a little bit about that. All these things have to happen before we get to rules of exponents in my classes. It takes several months, a little practice every day. We get there. And so the ln of x, if you want to know what exponent you put on top of e to get 5, that's the button you push on a calculator, the ln of 5. And the graph of the data that I've just shown you on the left is, I missed something I want to talk about, come back to it in a second. But, there's decay functions and there are growth functions. And generally speaking, you eventually realize that the ln of function is broken up into 2 parts. The decay values, the y values associated with fractions 1/3, 1/2, so on and so forth. And if you wanted to write the doubling function 2 to the x in e notation, then it would approximately be e to the 0.7x, approximately. Okay, so the y value at x equals 2, 0.7, is that value that you put on top of 2.71 to get the number 2. And very powerful function. I use Route 91. We're a school located in Upper Mass, and Route 91 is a north-south road, just kind of like the y-axis. And I like to use a kind of just a little analogy that if grandma was at 1 o'clock today driving north and at the function e to the x and e to the 1 gives us 2.71, And we know she's just past the border, the north-south border of Mass and Vermont. And her velocity would also be approximately 2.71. Because e to the x is its own derivative. And her acceleration would approximately be 2.71. So we know she's heading north. She's driving at 2.71 miles per hour. And that's why we study math, because I think that if I knew this, I'd want to go out and, help grandma. Maybe she's hopefully just pulling out of a rest area, but you don't know, maybe she needs some help. And that's why we study math, if anybody ever asks you, so you can help grandma. Good. All right, so if I wanted to know what 3 to the x was in E notation, if I could write it in E notation, what would it be? 3 to the x would approximately be e to the 1.1x. Right, because that's the y value at x equals 3. All right, so and again, one more time, reps for everything in math. You want to convert y equals say 9 to the x. Well, then you could write y is equal to e to the ln of 9 times x. You actually have that function. No approximation, it would be there, touching a finger. All right, so let's get towards the rules of logarithms. So after we get familiar with e to the x and ln of x, then we consider what's the ln of 6 without a calculator. If we didn't have a calculator, just to get a feel. Well, we could rename 6 as 2 times 3, and then we could change 2 to e to the 0.7 and 3 to e to the 1.1. And I think we would see e to the 0.7 times e to the 1.1 could have been expressed as e to the 0.7 plus 1.1 here. All right, and if you're just starting your algebraic studies, let's look at a situation that helps you see the addition of the exponents here. Let's just look at m squared times m to the 5th equals m to the 7th. And what I'm suggesting is m squared, we have m times m to the 5th, we got 5 of them here. And if you count them, you've got 7 of them. And I did that organically with 2 to the 5th. As just an example, could have been written as 2 squared times 2 to the 3. 2 to the 5th is 2 times 2 times 2 times 2 times 2, which is 32. And 2 squared is 4. 2 cubed is 8. And that does appear to be 2 to the 2 plus 3. Just a quick look at that as well. All right, so back to the rules of logarithms. Well, it appears that in multiplication, we got to have the same base. There are no rules for exponents unless you have the same base. Okay, so these are in the same base. And it appears that in that situation, it's addition. So 6 could have been written as the exponent you put on top of e. We don't put it there, but the exponent, the natural log, the exponent you put on top of e to get 6. We have to convert 6 into e notation. We've done that here. All right, and what that means is that there's a product. And that product can now be kind of shown as an addition situation, which makes life a little easier, especially if you're talking about big numbers. Okay, we're not talking about big numbers here, we're talking locally. And these approximations start to lose their accuracy over time. Not over time, but as x gets large, because exponential functions, small change in x, huge change in y. Right? But locally, not so true. So we can do this and at least get a feel for the rules. All right, so a product can be written as a sum of its parts, exponentially. So let's do a couple now. Now it's time to just practice a little bit and see if we can see the rules materialize. Oh boy, that's right. I gotta, all right, let's go back here and I'll use the eraser and I had some things written out. I'm not gonna start the video again. So the example I have over there is the ln of 2/3. What is that approximately? And you can certainly take a moment, pause the video. I'll just make a little space here. Then I'll move this camera back a little bit further. So what I'm suggesting here is that we change 2 to e to the 0.7 divided by e to the 1.1. And then we have a little division. Division can be expressed as e to the 0.7 minus 1.1. Right. So our answer is e to the negative 0.4, roughly. So 2/3, the element of 2/3 could have been written as 0.7 minus 1.1. And 0.7 is the ln of 2. Minus 1.1, the ln of 3. Oops, lost the marker. There we go. All right, so division implies subtraction. We have the same base. So now let's try another one. Let's do the ln of 2/3. Well, I just did that. I wanted to show that the ln of 2/3 is also equal to the ln of 1/3 times 2. Didn't want to write it that way. Well, yes, I guess I can say that. And so therefore that should be, given one of our previous rules, the ln of 1/3 plus the ln of 2. Now, what is the ln of 1/3? These are approximations now. The ln of 1/3 is approximately negative 1.1. And the ln of 2, maybe you've already got that down now, 0.7. And there's our negative 0.4 using one of our rules. Multiplication implies addition. And 1/3, remember, reciprocation. So the negative sign is reciprocation, which leads me to believe that I could show the power rule right now, but we'll do that with a different value. So you have the ln of 24. Let's look at the ln of 24. We'll use the rules of logarithms here in a moment, but let's actually develop organically an approximation. And so what is 24 equal to? 24 is equal to 4 times 6, which is equal to 2 squared. No, I don't want to do 4 times 6. I want to do 3 times 8, excuse me. So let's do 8 times 3, and 8 is 2 cubed times 3. Okay, so let's play with that. So now we have our 2's and our 3's, so we could say that 2 is e to the 0.7, and I'm cubing that, times 3, which is e to the 1.1, and ln is about the numerical activity of the exponents. So what do I see? I see a power to power, 3 times 0.7, 3 times 0.7, I'll show it that way, plus 1.1. Right, so that's approximately going to get us an approximate answer. These are approximations now. Approximations, 2.1 plus 1.1, 3.2. And we could come back over here to the ln function and see if that makes sense. So 3.2 is, well, this is 1.1. So 3, and this is going up slowly. So I've got it way down the board. So that wasn't the greatest one for me to pick, but I could see that it's headed there. So what do we have now? We have 3 times 0.7. Well, 0.7 is the ln of 2. And 1.1 is the ln of 3. Oh, okay. But remember, this was 8, right? And we did have 2 cubed. So it looks like originally that could have been here, 2 cubed. And we just noticed that, oh, that's the same thing as moving the 3 to the front of that exponential value because it's power to power. And these are kinds, it takes a little while to get a feel for this. It takes classes just several days, and we do a couple of these every day. In fact, it's on every test be on every test for the last month, 2 months of the semester. But it took us a long time before we actually got here. So I think this stuff just takes time. Now, what else do I have? Do I have anything else here? Oh, yeah, might as well do the change of base formula. Not that we use it that much anymore. But if it does help explain where it comes from, and that's not an easy thing to show, but realize that if you're gonna do logarithmic work, you gotta have things in the same base. And if you're gonna learn the same base of something, you might as well learn some exponential values associated with E. Gives you a lot of benefits by doing that. All right, so what's this thing? Going right back to what we said at the beginning of the video, log, the value of the exponent that you put in this case on top of 2 to get the number 3. That's the language associated with this. And you heard it again. And if it was new for you the first time, repetition's your friend. You heard it again, starts to sink in a little bit. How can I answer that? Well, I can change 2 to e to the 0.7 to the x, and 3 is e to the 1.1. Okay, so if I did that, then I really have ln of e to the 0.7 getting me e to the 1.1. Okay, and so that would then become 0.7x equals 1.1, right? Those have to be equal because the base is the same, and therefore we get 1.1 over 0.7. Well, what is 1.1 over 0.7? It's the ln of 3 over the ln of 2. That's your change of base formula, right? And you get a little feel for it. You start to get a little feel for something, and if you know where something comes from, yeah, it makes more sense. All right, so there's just a little work on rules of logarithms, and good luck.